All right, let's see. What were we talking about? I know we were talking about streaming the interface down to the computer and having all the horsepower up in the cloud. We talked about what's right, what's wrong about that. Um, I guess in the end, uh, distributed operating systems sound pretty good on paper, but seem to be riddled with problems. Yet it seems to be anti the way the rest of the world seems to be going. I mean, we seem to be wanting to take everything online, everything away from the hardware on our computer and things like that. But when we actually talk about an end user experience, we like having our data someplace else. But we don't necessarily like our computing someplace else because we like to have control over our performance. So I think there's some truth to that. Now, I guess maybe the better question to ask right now isn't so much that whether or not you want a distributed operating system, but is it even possible? Um, Given the stuff we've talked about, could we pull off a distributed OS? Is there enough bandwidth? Is there enough horsepower? Is internet in enough places? Is the internet fast enough in enough places where we could actually leverage something like this and have maybe even a hybrid? Maybe you're still running your local machine. Maybe you're still maybe our computers are very much like they are today. But what we've actually done is we've added a layer where some computing can be offshored. Does that kind of make sense? As opposed to the entire experience being in the cloud. We've seen this with some examples like SETI at Home and distributed.net. And we've even seen local examples more recently. There's a technology that Apple uses called OpenCL. That's in their, it was in, I think, Mountain Lion was the first one it was in. It might have been Lion, but let's just assume it was Mountain Lion. And then it's in Mavericks. And what OpenCL does is there's many computationally expensive things that are only math-based. So what OpenCL is it's a, let's call it kind of like a distributed operating system, but it lives all on your one computer. And what it does is it, kind of read it like this. It offshores computations to the GPU, the graphics processor in your machine. So there's some computations that so CPU is general purpose. GPU is, let's call, floating point math specific. So anything that the CPU would traditionally handle that's floating point math, you're actually better off sending it to the GPU. The GPU will be better at doing floating point math than the CPU is because it's specifically designed to do floating point math really, 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 really fast. Because everything it's doing is about putting polygons at certain points all over the screen. Does that make sense? So OpenCL takes a bunch of the computations off of the CPU's workload and puts it onto the GPU, because keeping in mind that your GPU is actually relatively underutilized most of the time. The only time you're really using your graphics processing unit is when you're playing a game. And it's, outputting a ton of graphics in a very short period of time. Your $600 graphics card is not working all that hard to display Microsoft Word on the screen. It's just barely, not even breaking a sweat. In fact, it's probably still in bed sleeping and still being able to display Word to the screen. So that's kind of a cool technology, that OpenCL. And even before that, there's a couple of different technologies that do this. One has ATI has one of them, and NVIDIA has the other one. But essentially, bridge graphics cards. So you can have more than one graphics card in your machine and bridge them together to create more power. So now you're taking, and I think you can go up to 4. I think is the max for one of the technologies. But you put, let's say, 4 graphics cards in the machine. I think they have to be the same graphics card or at least compatible with the technology. I want to say they have to be the same. And when you connect them together, they actually have to be hardware compatible. So like there's like a physical bridge you put on top of these guys. And what it does is it makes it like I want to say a quad core graphics card, but each of those graphics cards might have 256 cores. So now you just gave yourself 1,024 computational cores across 4 graphics cards. Are many games going to take advantage of this? Probably not, but you'd rather need it, not have it, not need it, than need it, not have it, something like that. But we see another example of that. But all these things are local. Okay, so they're local in your machine when we're offloading things to other pieces of hardware in your machine. The second we take something outside of your computer over the network, we're dealing with the limitations of the internet. And as fast as the internet is getting, it's not fast enough to really compete with our local stuff. We talked about this with the iDrive example, where in the early days of cloud computing, Apple thought, hey, it would be really cool if you just had this hard drive in the sky. And the hard drive showed up on your machine as a normal hard drive and had folders in it. You can drag and drop stuff in there. Downside is that file system, which worked just fine, was slow. Because every single time you drug a file in there, or opened a file from there, or saved a file to there, it was having to talk to the cloud. And it would delay. You'd hit save, and 8 seconds later, it would tell you, okay, you've saved your file. Oh, that took 8 seconds. We'd rather have it happen instantly, like the way Dropbox works. Okay, so I want to segue into special purpose OSs. Well, to kind of get the ball started, we might say mobile OSs. So like the operating systems that run on our mobile phones. So Android versus iOS. But let's create a little bit bigger, a bigger list than that to begin with. What other specific, so this is going to still be fairly general purpose. Just kind of the mobile version of it. We'll talk about the differences there. But what other specific operating systems, domain-specific operating systems, can we come up with that exist when we might not have necessarily considered that's an operating system?
Like a graphics calculator. Graphic calculator.
Graphing calculator? Oh, I was thinking he was playing like Yahtzee or something like that. It's like, at least you could do is turn your phone on and turn your sound on. Because it was making sounds like dice were rolling.
I hate those people.
Huh?
I hate those people.
My wife's
They
one.
have their volume all the way up and they're playing like the most annoying game.
That's my wife.
Really?
Like when we're driving the car, she's playing. Like she doesn't turn her. I like never have my volume on.
Yeah.
I just have it muted all the time. But yeah, I mean, she'll get text messages and she has all these like it's like the Norwegian cruise line anthem or something for a text message. She gets one text message. It's a 15-second song that plays. Nobody sends you just one text message.
Yeah, it was on like a train. I think I was playing a game. It was like,
Well, that would actually be better. Last time I was on a train, there was a guy sitting like right across the aisle from us, singing loudly for 4 hours.
really? No one like yelled at him?
He didn't look right. No,
Was it on a train? You just moved to the next car.
Yeah, I guess we could have. I think everyone was pretty nervous. Just nobody moved.
Was he good at singing or kind of decent?
Yeah, I guess kind of decent. I'm not into music, but I guess he wasn't like horrible singing. I could tell if something's horrible or not. But yeah, but he, something was a little off there.
Yeah.
Okay, what else? What else can we come up with for special purpose operating systems? What about TV sets? Don't our TVs have operating system on it? You have a menu button, bring some stuff up, right? Anything that can run software has an operating system, right? The operating system sits between the software and the hardware. That's its job. So you could say the same thing for VCRs and DVD players and Blu-ray players and Xboxes and PlayStation 4s. These all have operating systems, right? Some of them seem to be more general purpose operating system like, but they all have operating systems. What about a toaster? Depends on the toaster, right? Historically, the answer would have definitely been no, right? Now you got some pretty fancy toasters. I've seen a toaster that actually has an LCD screen with software running on it, and so you can pre-program how long you want to toast different things. That's a guesstimate. It's a guesstimate. Where if you toast Pop-Tarts and you toast toaster strudels, and your Pop-Tart has to have this amount of time for perfection, and your toaster strudel is this amount of time for perfection. That's unprecise if you're doing the little lever thing. With this, you can say 14.63 seconds. This one is 15.89 seconds, clearly. They are. There's blenders that do the same thing, where you can program different. It has like programmed in for different mixed drinks and stuff, where it tells you what to add. Like it has the recipe built into it, and then it goes through like different blend cycles to make sure it does it right or something. But most toasters, even a relatively fancy, let's take a coffee machine as an example. So, for instance, I have a really fancy coffee machine at my house. It has several buttons on the front of it, and it has an LCD screen. That does not have an operating system. The reason I say that doesn't have an operating system is there's not actually a piece of software running on it. It's all written in hardware. The buttons are my, equivalent to my mouse clicks or something like that, and then I have the one output thing that tells me what's going down. It says ready or press rinse to, that kind of stuff. So that's not an operating system. That's an interface to hardware. There's a distinct difference. Kind of make sense? Okay, what else? Anything else like completely out there that has an operating system? What are cars? Well, I have a Ford, and I have this whole computer sync screen. Inside this has a bunch of touch screen panel things, and it's like, look, my car doesn't have a steering wheel. I have a stick. My car has a stick. It's shipped that way? No. I put it on there. Before that, I didn't have anything. So some cars now have operating systems on there. Does an operating system? What's the point when something needs to have an operating system versus not having an operating system? If you're building a piece of hardware and you're having to make that decision, do I need an operating system or not? What's the decision-making process like?
How much stuff do you want to do?
Okay. So how much stuff do I need it to do?
If you're talking about like a computer system in a car, you're going to need to do like navigation, rear view mirrors. Okay,
we'll rate it for now. Number of things something needs to do. Okay, what else? We're going to come back to that line. I think it needs a little...
How general purpose your hardware is. So, like, if your piece of hardware is going to go into multiple different types of components, like a CPU, I guess.
Okay. How general purpose hardware is. I actually think these first two go together. Okay. What else? Maybe those are the most obvious things. You think you can throw things like cost in there? The second you start writing custom software for something, cost goes up. Now, for these first two, if I were to join these together, I might say something like, how complex would tasks be for a human to interface directly with hardware? Good example of this might be like a lawnmower. Like, could you buy a really expensive lawnmower that has a computerized screen? So let's take these like riding lawnmowers. I mean, some of those things are pretty fancy. They have built-in Sirius XM radio and things like that. You know, for like people who are like professional lawnmowers. Okay, but point is that if you mow a lawn, a couple of levers gets the job done. I mean, you got your speed, and you got this handle that says, how close to ground does the blade go, right? Okay, we're not talking about rocket science to mow a yard. You know, for the general purpose problem of mowing a yard. Once you start getting around the edges, then things get a little bit more scientific. That you do not want to put a weed whacker in my hands. Dangerous.
Is there a good story behind that?
Mm-mm. Not really. I mean, it's just, I look at it as a weapon pretty quickly, and taking out bushes, everything's a weed.
There's a video of a guy on YouTube getting whacked with a weed whacker.
Really? Like somebody attacking him with it? Or?
No, he did it on purpose. I think he was probably really drunk or really high, and they held up an electric weed whacker and got him right across the nipple.
Now, what I always thought was interesting is like, you know how they sell like the special blades for weed whackers that like don't break and stuff like that? Doesn't that make it like more dangerous? You know, because like part of like with the string is it's supposed to break when you get close to stuff. All of a sudden you're like ripping off gutters.
Well, it's like going for like huge brush and small trees.
Mm-hmm. I think you could solve any problem with a riding lawnmower. Go right up against the edge of the house. It's like, well, what about my plants? Don't put them there. That's part of the lawn. Anything that's not structural is lawn. But in any case, a lawnmower, couple of little handles, mechanical hardware thing, and you can mow a yard, right? So you don't need an operating system where you have a push button, you know, or maybe even like a nice graphic screen and a slide thing and all that stuff that adjusts the level, you know, just like you probably don't really need an operating system for your toaster, right? You know, it just looks cool for 5 seconds and then all of a sudden it's useless. It's like, oh, well, I have a $800 toaster that has an operating system on it. And okay, well, I stole this out of a garbage can, and it's the best toaster I've ever had. Pre-seasoned.
They have robotic lawnmowers now, too.
Mm-hmm. Just like the vacuum cleaners.
Yeah.
Yep. I wonder how accurate those are.
I read about them. They're kind of accurate, but they take a while because they have a really small blade on the bottom.
Okay.
They're not big machines.
I gotcha. So it's like a Roomba vacuum cleaner thing, but maybe a little bit more, you know, it needs to be high enough off the ground to be able to go through grass.
No, it's pretty big. And
Yeah.
small blade, though. So it's kind of, it does it for you, but it will take a while. And some
Who
of
cares?
it's solar power, which is kind of cool.
Yeah.
So it keeps charging itself.
It's kind of cool. Right.
Very expensive.
Are they like 1,000, 2,000?
2,000.
2,000. Except you leave your house while your lawn's being mowed and come back, somebody stole your lawnmower. That's what happens when
Or
you
your lawnmower kills somebody.
That would be. I don't think funny is the right word, but that would be a funny news story. That would be a funny news story. It's like, new robotic lawnmower or death machine.
Toddlers down. Jumped your yard, went into the neighbor's yard. Toddler play day.
Just have a mother on the TV screen. She's inconsolable. There was birthday cake and ears everywhere. Birthday cake and ears.
That's pretty awful.
Oh, that's recorded. Okay, so I really think this probably captures it. How complex a task would be for a human being to accomplish using just the hardware, right? Interfacing with the hardware itself. That's the job an operating system solves. Okay? Now, you can start getting into, the general purposeness of the hardware, but even then, let's take a lawnmower, you have a blade. Well, there's lots of other things that might have a spinning blade, on them. So, just because it's general purpose hardware doesn't necessarily dictate that it requires an operating system. But, at the end of the day, I think the simplest answer is, if the task would be too complex for a human being to solve directly, let's write an operating system to solve it. Now, can we have a computer without an OS? Well, starting point is what's a computer?
Something that solves a problem.
Okay. So a lawnmower is a computer? It's a fancy enough one. Where does a computer start and a machine end or something like that? At what point does it actually become a computer? Or is computer really a pretty generalistic term? Computer itself is a pretty generalistic term. Human beings use it fairly specifically, right? When somebody says, "Oh, what kind of computer do you have?" Your follow-up question is, what do you mean? It's not like, well, I mean, this is one of my computers. this remote. I mean, I compute with this. I change channels, and it solves a problem, right? But we know in context, the computer means one of these guys or one of these guys, something like that, right? Can we have one of these guys without an operating system? Okay. How would you use it? Let's take one of those guys then. Can we have one of those without an operating system? Well, can we have one of those guys and use it without an operating system? I mean, hey, I could wipe this hard drive. No OS, still a computer.
I'm sure if you send like specific electrical impulses of some sort through other hardware, you can do it that way.
Okay, so basically mimicking what the operating system is doing, whatever that means, right? Well, in our early computers, were our early computers this size? Were they that size? How big were our earliest computers?
Is that the Mac in a box?
Depends how far back you go for a computer.
Calculator?
So this was at Penn State. This is something called EDVAC. That's a computer. That's a computer. UNIVAC. This guy's working on it. Now the funny thing is, this is when computers started getting smaller. You had computers before this that were the size of a gymnasium. This is the size of a large room. This guy. Why were computers this big? And how did we go from this to this? What happened? Did these computers have an operating system? These room-size ones. Did UNIVAC have an operating system, do you suspect? So this is kind of the giant version of my coffee machine, right? Where I said there's buttons and stuff, but no real software. You're interacting directly with the hardware. Now the VAC part of these stands for vacuum tube. Probably misspelled that, but I'll fix it. So vacuum tube is a device controlling electric current through a vacuum in a sealed container. So you can turn it on, you can turn it off. What does that sound like to you? Binary, digital. It's digital logic. So imagine you had to operate a computer one bit at a time. Well, how would this work? If you had to build, a computer that people needed to interact with, but you didn't have an operating system. And I'm saying we had to do this one bit at a time. Let's go back to our early computers. Based on what we know in here, what is a CPU? What does a CPU actually do? Okay, so a CPU has a list of magic tricks that it knows how to do. So we give it a identifier that says do magic trick 1, and it does magic trick 1. Then do magic trick 2, it does magic trick 2, right? Okay. How many magic tricks can a processor do? More than a couple, less than a zillion, right? Okay, because what it tries to do is it tries to be as general purpose as possible. So it breaks things, it breaks your different tools down into, smaller widgets. So it's kind of like having a toolbox where you're somebody who builds a house and everything that you need to build a house is inside this toolbox and you just have to use the tools in the right order and that kind of stuff. So that's kind of how a CPU works. Well, let's say that the number of the different unique commands the CPU understood was represented as an 8-bit number. So 8-bit unique commands. How many commands is that? How many unique commands are there if it's an 8-bit processor? Maximum. So I uniquely identify each command by 8 bits. So how many unique 8-bit numbers are there? Should be one of those off the top of your head computer science numbers. 256. 256 unique commands. 2 to the 8th power. Make sense? Okay. So we can have up to 256 unique commands on an 8-bit computer. Now, let's say that you were writing a computer to solve very simple problems. Let's just say a calculator, the early calculators. So you're going to build a computer that can do addition, subtraction, multiplication, and division. How many commands does it need to know how to do? How would you pull off addition, subtraction, multiplication, and division at the bit level? How would you even input it? Let's say you wanted to input the number 5. How would you input the number 5 into a computer? Physically. How would you physically input it? We don't get to just open up the calculator app and type in a 5 and then hit the plus sign. Let's go to town. If you were building a computer completely out of hardware, no operating system, how would you get the 5 into the system? Okay, so if we're doing an 8-bit computer. So 8-bit computer, just for doing calculations, for math. So basically a simple calculator is what this guy would end up being, the size of a gymnasium, more than likely. Okay, so what would this guy do? Well, we're going to have input 1. Input 1 would be a 8-bit, say, integer. So we control that with 8 vacuum tubes, right? So 8 vacuum tubes. Same thing with input 2. So now we have 16 total vacuum tubes. So you go over to your input wall, you start turning on tubes. Right ones light up, wrong ones don't light up, so now you have your numbers. So what is a 5 in 8-bit binary? How would you represent a 5 in 8-bit binary? Well, how would you represent 5 in binary? (101). This is the ones place, this is the twos place, this is the fours place. So 4 times 1 is 4, plus 0 times 2 is 4, plus 1 times 1 is 5. Does that make sense? And we pad it out with our, so we have a total of 8 bits. There's our 8 bits. So our first 5 vacuum tubes would be off, then turn one on, then leave the next one off, then turn the last one on. That's how we would represent 5. That make sense? You know how to convert from binary? Why? That's so important, Dane.
Yeah. Why is that important?
I mean, that's like beginner computer science stuff.
Yeah, that was a while ago.
No. When you learned it, you're supposed to remember it.
It's not gonna happen.
Voltage, you know how to do it? I don't even know, why are people even in school these days?
Jobs required. They want that sheet of paper saying you have a degree.
What jobs? Flipping burgers?
No. It's got a personality.
It's got a personality. All right, so we're going to have 5 in an 8-bit binary number. Then let's say we have 13 in an 8-bit binary number. So this is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place. So we don't want that. So we're going to have an 8 plus a 4 plus a 1. So that is 1, 1, 0, 1. That's 13, right? 8, 9, 10, 11, 12, 12, 13. Tack on our extra zeros there in the front. So there's our 8-bit representation of a 5. Here is our 8-bit representation of a 13. Well, how do we actually solve that problem? Well, we need to switch back and forth here a little bit. All right. Let's put them all zeros right now. How do we do math? Well, we're doing addition. Let's say we're adding these two together. So we take 1 plus 1 is actually 2, correct? You got that one, Dane?
I think I can handle it.
Okay. But is 2 a legal digit in binary? No. Zeros and ones are only allowed. So we're going to say that is 0. I need to give myself a carry list here. Carry the 1. 0 plus 0 plus 1 is what? That's 1. Dane's on a roll. Dane is on a roll. Okay, 1 plus 1 is 0. Carry the 1. 1 plus 0 plus 1 is what?
2.
2, which is 0. Carry the 1. I got this. All right. 0 plus 0 plus 1 is 1, and then all the rest are zeros, correct? So this is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place. So this is 16 plus 2, which is 18, is 13 plus 5, 18? Yes. The correct answer is yes, it is. All right, so we just did binary math. So if these are all my inputs, so I had 8 vacuum tubes to represent my input, and I had 8 vacuum tubes to represent my output, now I need to actually create a circuit, a hardware circuit, that goes through, and takes all of the individual vacuum tubes. So we really have 3 different states, right? We have a 0 and a 0, which is always a 0. We have a 1 and a 1, which is always a 0 with a carry bit. And we have a 1 and a 0. I guess we could say 4 states. We have a 1 and a 0, which is a 1, or a 0 and a 1, which is a 1. Does that make sense? So we have 4 different states that we need to be able to handle. If they're both 1s, the answer is 0 with a carry bit. Well, now that carry bit is now a 3rd input. So we need to actually support a 3rd input now to our program. Do you kind of see how even just addition gets a little bit more complex? So you're having to build this thing without transistors. That's what really happened between old computers and our modern computers, is we replaced all those vacuum tubes and stuff like that with transistors. That's something that had an on or off state. All right? So if you were building a computer just to do add, subtract, multiply, divide, we could already see that it's going to be fairly complex, right? What's the limitation of this computer? If I just showed you that right now we have a computer that can only do addition, so you can even replace the word math with just addition. What's the limitation here? If you were selling this at Best Buy, which is where I fear some of you might end up. If you were selling this at Best Buy and you were telling somebody the features of this computer, what would you tell them? Well, if you were at Best Buy, you'd probably just lie to them. But if you were a good Best Buy employee, what would you tell them? What's the limitations? You can only add 0 to 255. 0 to 255 are your maximum input sizes, right? And what about the output size? Well, you're going to have to give yourself an extra output bit if you even want to be able to add those two together, right? Because 255 plus 255, now we need one more bit to represent that, right? Okay? So, now how often do you need to add numbers together that are greater than 255? Would you say often? I mean, if you're in that smaller hundreds number, a lot of times we just do it in our head, right? Okay, so how useful is that? Not that useful. So now we need to get even bigger. So what if we were representing size of int? And we'll pick up here next time, but what if we were representing, let me just actually write a slide to say that. What if we were representing Java's size of int? So that's 32 bits. So we didn't even talk about representing negative numbers yet. That make sense? To even get something general purpose, you can have vacuum tubes all over the place. All right, we'll pick up there on Wednesday with a quiz for converting binary numbers. So go back and watch this video and learn how to do that.